good news about it. When you work with a sphere, there is no slant height. There is no height. There's no base area. There's one thing you need for a sphere. And that's this piece right here. What do you think that's called? There you go. That's the only thing you need for a sphere is a radius. All right? There is no base, no slant height, no Mission Impossible height. If you know the radius of a sphere, you're in pretty good hands. Here's why. Let's start surface area of a sphere. Again, remember surface area. I know we took a quiz on it, but we didn't include the sphere. Everything on the outside, right? We're not filling it up. Everything on the outside of the sphere. This is the one and only one formula you got to know. It's not on the formula sheet. So you got to come in next Thursday knowing it. And here's how I remember it. It's 4 circles. The formula, 4 circles. 4 circles. What am I going to attach to it if I say circle? Pi r squared. There you go. It's 4 circles. And also make a little note so you guys also remember, hey, this is not on the reference sheet. Okay, not on the reference sheet. Before we move on, look at the formula for me. What's the only value you need to substitute in? Radius. That's it, right? 4 pi, and then you need the radius, and you got the surface area. All you need is the radius. All right, keep that in mind. All right, let's go to this first one because you know how I'm doing it. I told you this is going to be a little bit tougher the second half. I'm just not going, hey guys, the radius is 3. What's the surface area? We're not about that. All right, it's a waste of time. Circumference. Circumference of a rubber ball, aka a sphere, 20 pi. What's the surface area? Okay, again, I need the radius. All right, what did I give you? Circumference. I'm not going to ask you to dig deep and remember unit 10 because the darn formula is on the formula sheet. Go to your formula sheet. Circumference is on there. I want you to become more and more familiar with this formula sheet as we head into the Regents next month. Circumference is on there. Look under circle. Everyone see it's area for one of them, and then everyone sees C for circumference. And everyone knows the one we've been using, pi d. If you want to use 2 pi r, you can, but pi d. So I'll start with that formula. Well, that one doesn't have radius. Zip it. It's got diameter. We'll be fine. Okay, we'll be fine. All right, substitute in the 20 pi. Circumference is 20 pi. Substitute that in for C. 20 pi equals pi d. And it seems like this happens all the time, right? Pi's on both sides. See ya. I'm not going to assume this. I want to check. All right, what's my diameter length then of this rubber ball? Diameter length. Ooh, we'll go again. Oh, there we go. Shara, diameter length. What is it? 20. Good work. But I need radius, so we'll cut that in half. Radius is 10. And now let's find the surface area. Leave it in terms of pi. I know there's no rounding directions. Leave your surface area in terms of pi for me. So 4 pi r squared, only formula I need to remember. And plug in that 10. And then I got a bonus question for you guys on this one before we move on. A little bonus. All right, in terms of pi, what's my surface area? In terms of pi, Stellan? 400 pi. Good. Here's my bonus question. Units for this one? Squared. Nice! Nice. Centimeters squared. Why squared? Because we're finding surface area. Again, surface area. Nice. All right, good work, kids. Volume of a sphere. Thank goodness that formula sheet has this one because this one's a pretty involved one. This one is a tough one to remember if we had to memorize it. But it's on the formula sheet. Everyone go back, take a look. Volume of a sphere. Whoa, 4/3. Yikes. 4/3 pi r, not squared, but cubed. Woo! Woo! But again, what's the only value I need to substitute in? Radius. That's it. If you're dealing with a sphere, if you know the radius, you're going to be in good shape. All right, next up, number 2. I'm telling you the volume. What's the surface area? All right, I'm giving you the volume as 36 pi. What's the surface area? We still got to find what value? Radius, right? That's the whole point of, you got to know the radius before you find anything. All right, so volume equals 4/3 pi r cubed. Substitute in the 36 pi. Hopefully many of you are getting rid of the pi's right away, so we don't have to deal with it. So you're left with 36 equals 4/3 r cubed. Good work so far. I got to get r by itself, though. How are you getting rid of the 4/3? 2 ways you could get rid of the 4/3. 2 ways. One way I could get rid of it. Lauren? Divide both sides by 4/3. Anybody doing multiply? What do you got to multiply by then if you do multiply? 3/4, the reciprocal. Good. So either way, get it done. Divide by 4/3 or multiply by 3/4. And then a quick reminder on what to do next, because we've only done this once. So no matter what you do, you're getting 27, right? 27. Whether you divide by 4/3 or multiply by 3/4. All right, now again, a reminder on how this works. If this was squared, I take the square root, but it's cubed, so I take what's called the cube root with the 3 right in there, and that is located on your toolbox. Okay, if you can't find it immediately, scroll up to the top. It should be right the second one from the top. It says nth root, and you can make that anything you want. Make it a 3 in this case. So we find the radius is 3, but we didn't answer the question. We got to find what's the surface area. All right, so let's go now. The surface area, 4 pi r squared. Leave it in terms of pi again. Go ahead and leave it in terms of pi. Ooh, and Henry, what do you got in terms of pi? When you're ready. Yeah, for the radius. What's the question? The question is find the surface area. So now I need to substitute 3 into the surface area formula for radius. 12. Just square the 3. Remember, it's 4 pi r squared. 4 pi r squared for the surface area. 36 pi. Thank you. And this is, I know some of you are, oh my God, it came out to be the same as the volume. It's not the same. What's surface area? Everything on the outside, volume's everything on the inside. And these are 2 different types of units, squared and cubed. So not the same, not the same. The 36s, it's about all the same. Any questions before we go into those real life examples that we all love? All right, it's hard to do it with spheres. The best you can find, here you go, volleyballs. Right? There you go, volleyball, shapes of a sphere. FYI, when you purchase a volleyball not fully inflated, FYI. When they're not inflated, they have a volume of 180, but when they're fully inflated, they have a volume of 294 cubic inches. What's the difference in the radii? That's what I'm looking for. How much does the radius increase from the partially to the fully inflated? Yeah, that's what I'm looking for. All right, looking for the difference in the radii. That's what we need to solve for. There is one thing that happens here that has not happened to us yet, and I don't want you to get nervous. So let's talk about the partially inflated. Let's see, what's partially? 180 for the volume. And volume is 4/3 pi r cubed. All I did was substitute in the 180. Here's, everyone see what's happening? First time ever. What does not cancel on both sides? Don't cancel them. All right, it's not automatic. The 180 does not have a pi. Don't put it with it. So don't cross the one out on the right. You're eventually going to have to divide by it. So you can divide by it in the first step or the second step. You either get rid of the 4/3 first or the pi first. Your call. And then get rid of the other one in the second step. So I'm going to let you guys work right now. for both the partially inflated and the fully inflated. And we'll see if we come up. Do not round those decimals at the end because we need to subtract them. Don't round the radii. Check out the radii here, please. Make sure we got the radii correct before I ask somebody what the difference is or the increase in the radii from partially to fully inflated. Ready to go here? Nearest tenth. How much does the radii increase from one volleyball to the next? Oh, what's my increase there, Dylan? Nearest tenth? 0.6 inches. 0.6 inches that radii increases from when it's bought to when it's fully inflated. Questions going? All right, well, let's talk about, we talk about a sphere. What about a hemisphere? I want to do volume first, though. Volume first. If you're getting ahead of me, surface area, you're going to forget something. All right, so stay with me here. Let's do volume first. Volume. Well, hey, help me out. Help me. I need a little help. I know the volume of a full sphere is 4/3 pi r cubed. That's a full sphere. This is a hemisphere. So what do you think I'm going to do to this volume? Cut it in half. So either you can show it's being divided by 2, or I like to do this, just say I'm going to multiply it by half. But if you want to show divided by 2, that's fine. But I got to cut it in half at the end. Okay, got to cut it in half. So yes, there you go. Hemisphere, cut your volume in half. So 1/2 times 4/3. Make sure we're using 14 for the radii cubed. Make sure it's cubed, not squared. It's on the formula sheet. Nearest 10th here. Nearest 10th. What's the volume? Nearest 10th. Dylan, back to you. 2 for 2. Got it. 5,747. If you want to put the 0.0, because it is nearest 10th, that's fine. If not, though, it's still good. All right. We're ready for surface area now. Okay, I hate to break it to people if you went ahead here. I know the surface area is 4 pi r squared. And you're like, oh, volume, we cut it in half, so I'm going to cut it in half in here. And you are correct. But you're missing something. You're missing something. First, surface area. Just plain definition. Everything on the outside, right? When you do 4 pi r squared divided by 2, you are finding that surface area right here. What am I missing? The bottom. You're not counting. When you do that, you're just counting the top part here. That's the area you're finding, but I need everything, including the base. So we need to add to that, all right? Because all you're finding, everyone agree, you're just finding the top part right now divided by 2. You need to count the base. So now I need to add in. All right, here you go. What shape's the base? What did I forget to add in, eh? Circle, which has an area formula of pi r squared. I had a couple clever students first period say, Mr. Carlino, can I just put 3 pi r squared instead? Because that's what, right? That's 2 pi r squared, and that's another one. So you could, but I just don't want to give you another formula to memorize. So I'm just telling you, you have to add on the circle. All right, that's how I'm going to teach you. You have to add on the circle to what you divide by 2. All right, so be aware. Volume, just divide by 2, but surface area, got to count the circular base. And now we can plug in that 14 again. Don't forget about the circular base. And when you have that surface area, let me know. Round it to the nearest 10th. Oh, Brendan, what do you got, boss?
1,847.
There you go. And this is square feet because we're doing surface area. Good. All right, so just guys, just don't forget that. Surface area of a hemisphere, everything. Just don't do the dome part. Don't do the dome part. Do the part on the bottom. See that one? There was a guy riding his bicycle. His son must be going to Eagle, must be riding your bike to school day. And the kids, there's like the kid's bike is just literally attached to the dad's. So the kid is doing zero work. Just attached to it. Like, what do we do? What are we teaching our kid there? Learn to ride your bike. Learn to ride your bike. All right, anyway. Sorry about that. Sorry. It's odd too. It's like just we're literally connected to the bike. All right, moving on. Sorry. Last thing I need to show you, and this just deals with volume in general, has nothing to do with the sphere. It's called Cavalieri's principle. It's just named by the mathematician. I forget his first name, but his last name was Cavalieri. Here's what it says. You guys are familiar with pizza boxes. All right, you're familiar with that. So let's say on this group right here, I have a neat stack of pizza boxes like I do in that first diagram. All right. Over here, this group, I give them the same number of pizza boxes, but they're slanted a little bit, like this one here. All right. This group right here, I give them the same number of pizza boxes that I did the first group, but as you guys can see, it's a hot mess. All right. Some of you can probably relate. All right. It's just a hot mess of pizza boxes. And I asked you guys, which one has the biggest volume? Which one has the greatest volume? You'd probably pick the group that's got the neatly stacked one, just by looks. But you know what the answer is? They all have the same volume. All three have the same volume. All right? We don't go by looks. Here's the reason why, and here's what this little principle is saying, why they all have the same volume. If the area of the bases, and you don't have to write this, I'm just showing you. We always called it capital B. If the area of the base are all the same, and the heights are all the same, They all have the same height because it's the same amount of pizza boxes. If the area of their bases are the same and the heights are the same, you know what? All three have the same volume no matter what they look like. All right? You don't go by looks and say, oh, well, that looks bigger or that looks more organized, so I'm going to say that has the bigger volume. No. As long as their area of their bases are the same and their heights are the same, they're going to have the same volume. That's also true. Take a look down below here. Even if they're two different figures. This one right here is a triangular prism. This one right here is a rectangular one. And you're like, oh, they can't have the same volume. They're different. No. I'm going to tell you, the area of this triangle is the same area as that rectangle. And they have the same height. So that means they have the same volume. All right? Don't go by the looks. Just because they're two different figures doesn't mean they have two different volumes. As long as their base area is the same and their height is the same, they will have the same volumes. Look at the example I give you next, please. Triangular prism, rectangular prism. Oh no, they're not going to have the same volume. They're different. Baloney, watch. Triangular prism. Find the area of that triangle for me. Find the area of that base. Capital B. 1/2 times 4 times 2, right? Area of a triangle. What's the area of that base? What's the area of that triangle? Where are we going on this one? Alyssa? 4. What's the height of that triangular prism? What's the height of that one? Alyssa, again. 13. All right. Now go to my rectangular prism. If somebody's going to keep telling me they can't have the same volume, they look different. All right, ready? What's the area of this base now? Area of this base? Oh, 3 for 3, Alyssa. 4. And what is the height of this prism? Oh, there we go. Something a little different there. Jonathan? 13. Same volume. Same base area. And I don't even need, did we even calculate the volume? We didn't need to. As long as they have the same base area and the same height, same volume. But they look different. It doesn't matter. Same base area, same height, same volume. All right, what about my cones here now? Cone and cylinder. Let's start with the cone. Can't do length times width here. We got to do pi r squared, right? Because it's a circle. That's a 7. It's hiding over there. I'm sorry. That's a 7. That's hiding. So leave your answer in terms of pi for me. What's the area of that circular base on the cone? Leave your answer in terms of pi. The cone, and again, I am not finding the volume with you. I don't want to find the volume. What do you got over there, Simon? What's the, in terms of pi, what's the area of that circular base?
49 pi.
49 pi. And I'll stick with you right here. What's the height?
13.
13. Good. All right, let's go over here to the cylinder. What's my area of the base here? Pi r squared again. It's a circle. What's the area of that base of the cylinder? Keep rolling here with me. Good job so far. We'll keep going. Oh, Simon, back to you.
Also 49 pi.
Also 49 pi. Oh, wait a second. I think they're going to have the same volume. What's the height, Simon?
6.
All right, they don't. They got to have the same of each. Okay, so different volume. Everyone's seeing how this works without even finding the volumes. I don't want you to find them, but we can tell if they're going to have the same one or not. And then this is an old Regents question. 2 stacks of 23/4 there. One stack forms a cylinder. The other stack does not, obviously. I don't know what that forms there. Why are the volumes going to be the same? Why are the volumes going to be the same? All right, well, all right, talk to me here. Let's talk about their base area. What is the base? It's a what? It's a quarter, right? It's a quarter. They're all quarters. It's not like I put a dime here or a penny. The bases are both quarters. Agreed? So they're both going to have the same area. Yes? I hope. I don't think they have different radii, but All right, I guess it could be a smaller one, but I'm assuming they're all the same size quarters. So base areas are the same. Base area is the same. And I'm just going to put here their quarters. Now, what about the height? Those heights don't look the same. Baloney. They both have how many quarters in it? 23. It's not like one's got 20 and the other's got 23. Yeah, that would be different heights. They have 23. I don't care if this is slanted. It doesn't matter. They have 23 each. They're going to have the same height. Same heights, 23 quarters. So that's why they're going to have the same volume. Okay, base areas are both quarters, and then they have to have the same heights if there's 23 in each of them, each stack. All right, are we all good? All right, get going on the